Hello and welcome to the next video. In this video we will study about some of the physics of why an EMF is induced when we change the flux. So let us recap quickly. We studied from Faraday's law that an EMF is induced whenever we change the flux of the magnetic field in a region. And we know that flux of a magnetic field is nothing but B into A. So there are two ways to induce an EMF, or there are two ways to change the flux of an inner region. One is to change the magnetic field and another is to change the area. So the A shows the first example where we are changing the magnetic field which is passing through this loop, or the strength of the magnetic field. So as we take the magnet closer and closer to the loop, the magnetic field or the intensity of the magnetic field inside the loop increases, and that is how I am changing the magnetic field which is passing through this loop, and in that way I am changing the EMF. So one question is, why does a change in magnetic field in a region induce an EMF? And to the answer to that question can just at a conceptual level or at a very basic level, the reason can be understood as follows. If you remember our discussions of the magnetic field, we had said that magnetic field and electric field are the two sides of the same coin. It just depends on the frame of reference of the observer, whether he sees a field in a region to be a magnetic field or an electric field. It depends on the motion of the observer relative to the field itself, or relative to the charge, but they are interrelated to each other by motion. So that is why whenever I change a magnetic field in a region, an electric field is induced. Okay, so another way of writing this induced EMF, we know that EMF is nothing but integration of, for a closed loop it will be integration, the potential is the integration of E into dl. Okay, so if I can rewrite this Faraday's equation as integration of E dl, or induced EMF, or integration of E dl is equal to d phi by dt with a negative sign on it. So this tells us that whenever there is a change in magnetic field in a region, an electric field is induced in the region, and that induced electric field is the cause of this potential, induced electric potential. Okay, so this is one of the ways in which I can induce a EMF. Another way is to change the area of this loop itself. So I can start increasing or decreasing this loop, or I can do that in another way. Suppose I have a straight conductor and I start moving it in the magnetic field, say in this direction. So if I move this conductor in this region, what I am doing is I am changing the area of, it can be thought of that I am changing the area of this circular loop. Excuse me. Although even if I don't have a loop, I have just a straight conductor which I am moving it in a magnetic field, then also there will be an induced EMF across this conductor. So what is the cause of that induced EMF? The cause can be found out if we go back to the very basics of magnetic field. Let us study that. So in a conductor, why is it called a conductor? It is called a conductor because it has lot of free electrons inside the conductor. inside this conductor, which can carry current or charges, electric charges. So it has a lot of free electrons, and when I am moving this conductor along this direction, okay, apart from the random velocity, if I move this conductor with a velocity v, I am giving the free electrons an average velocity of v along this direction. So the electrons will also start moving along with the conductor in this direction, and the average velocity of the electrons will be equal to the average velocity of this conductor, which is equal to v in this direction. And if you remember our magnetic field discussions videos, we had known that if I move a charged particle in a magnetic field, okay, if I move a charged particle in a magnetic field, it experiences a force of F is equal to Q V cross B. Okay. So these electrons will start to experience the force due to the motion of these electrons, because they are moving in a magnetic field. They will start experiencing a force which will be equal to Q V cross B, and they will start moving towards one of the end of the conductor. So suppose I have not done the calculation or the right hand thumb rule. You can apply the right hand thumb rule. Let us apply the right hand thumb rule. So V is in this towards the right, and V is towards the right, and magnetic field is going inside the plane. So yes, my assumed direction, if you apply your right hand thumb rule, the electron should go to this direction. Remember that electrons are negatively charged, so they will experience a force opposite to the direction of the positive charge. So if you apply those concepts, you will find that all the electrons start to move towards this end of the conductor. Now when these electrons are starting to move towards this end of the conductor, this end of conductor will slowly start getting negative charge, and this end will start getting positive charge, because the electrons have started moving from here to here. So this end is getting negatively charged, and this end is getting positively charged. Excuse me, I have some cough, so please bear with me. So as the electrons flow from here to here, an electric field starts to being set up, and because there is a positive charge build up, now the electrons are experiencing a force, magnetic force B along this direction, but because gradually electric field is also getting set up, because the electrons are moving toward this direction. So because of that electric field now, which is being induced, okay, this is the induced electric field because of the force. So because of that induced electric field, the electrons will start to experience a force in this direction. Okay, so the magnitude of the electric field developed will be such that, so the force along this direction F will be equal to Q into E. Agreed? So the magnitude of this electric field which will be set up will be such that the magnetic force and the electric force balances. So the electrons will keep on moving to the other side till the induced electric force is enough to stop more electrons from going to that side, or till the time both the magnetic force and the electric force balances out. Okay, so that will happen when Q V cross B will be equal to Q into E. So Q gets cancelled. Okay, and I get what is the electric field inside this conductor. So if electric field inside this conductor is E, what will be the potential difference? The potential difference across this will be just nothing but E into L. Okay, so E will be equal to just E into L, or it will be L into V cross B. just replacing the value of E, putting the value of E from here to here, I will get E is equal to L length times E or length times V cross B. So this is the induced EMF. Okay. So this is the induced EMF which I have got. Okay. So is the Faraday's law consistent with this? Okay. So this is the physics behind the induced EMF. Why there is an induced EMF when I move the conductor or change the area? Okay. So is it consistent? Because my Faraday's law is giving me a different formula. E is equal to minus d phi by dt. So will I get the same formula if I apply Faraday's law? Yes, I will. And quickly let us look into that. So suppose the magnetic field again is B. Suppose this distance is x and the length of the conductor is L. So the area of this loop is x into L, correct? So the area of this loop is x into L. Area is equal to, x into L, and so phi will be equal to B into area. So B into x into L. Okay. Okay. And so E will be equal to d phi by dt according to Faraday's law. Okay. So which is equal to B into x into L into ddt. And because I am not changing magnetic, this is my second type where I am not changing the magnetic field but I am changing the area, correct? So B is constant and also length is constant. Okay. By moving this side I am not changing the L. What I am changing? I am just changing the x. Okay. I am decreasing the x as I move my conductor towards my left. So x is the only variable, L is constant, B is constant. Okay. So I put, because they are constant, I take it out of the differential sign, BL into dx by dt. So this is nothing but dx by dt is nothing but V. So BLV, which is the same as this equation which I have got for the induced EMF. And so Faraday's law is justified, and we also know that why there is an induced EMF, because when I take the conductor or move the conductor, the induced EMF is because there are electrons inside that, and whenever there are electrons inside the conductor and I move the electrons, whenever I move the charged particles in a magnetic field, they will experience a force, and that force translates into a potential difference. Whenever I redistribute charges, there is by applying a force, there is an induced EMF, or there is a potential difference set up in that region. So this allows us to continue to our next topic. Let's see. Next topic is self-inductance. So self-inductance. So what is self-inductance? Self-inductance. Sorry for the bad handwriting, but suppose I have a current carrying loop here, single current carrying loop of radius r. The carried current is I, and I know that magnetic field B is equal to mu naught I by 2r, correct? And another case, I have a solenoid. So if I have a solenoid, then the magnetic field inside any point, say this point here, is mu naught Ni, where N is the number of loops per unit length. If you go back to again some of the previous videos, you will get a derivation of this. So B is equal to a magnetic field inside a solenoid. Solenoid is nothing but a lot of turns wound together. So B mu naught into number of turns per unit length into I. So what is flux? Here in this case, flux is nothing but B into A. So mu naught by 2r, mu naught into 2r into area. Area of this is pi r square pi r square into I. Okay, so this can be simplified as not full, this is r, this got cancelled, so mu naught r by 2 into I. And what is the flux through one loop? Okay, through one of the loop here. So the flux through one of the loop is flux through one loop is mu naught n into area of one loop. Area of one loop can be written as pi r squared. Okay, so this is the area of one loop into I. Okay, so if the flux through one loop is mu naught n pi r square I, what is the total flux through the full solenoid? So the total flux through full solenoid is the flux through one loop. Flux through one loop is mu naught pi r square. I will write I here. So this is the flux through one loop multiplied by the total number of loops. So the total number of loops is number of loops per unit length, which is denoted by small n, into the total length of the solenoid. Okay, so again repeating, the flux through one loop is mu naught n by pi r square I. Okay, mu naught n into pi r square, area of one loop, into I. So flux through total loop is the flux through one loop, which is mu naught n pi r square I, multiplied by the total number of loops, and total number of loops is number of loops per unit length, which is small n. Small n is the number of loops per unit length multiplied by the total length. So this is the flux. So I can, let me simplify it. So mu naught n square pi r squared I. Okay, so notice that is whenever we have circular loops, the flux is dependent on a geometrical parameter. So here geometrical parameter is mu naught r by 2, which is dependent on the radius of this circle, and here the geometrical parameter is mu naught n square pi r square L, I have forgotten. Okay, L into I. Again here, again the phi depends on a geometrical parameter and the total current which is carried here. Okay, so in general I can write phi is equal to Li. Okay, well, L is called the inductance of these coils. Okay, L is called inductance of this coil, and it depends on the geometry. Okay, so L for a circular loop will be mu naught r by 2. You can be asked derivation. Derive the formula for L of a long solenoid. So this is the derivation of the L for a long solenoid. L is equal to, because we know that phi is equal to Li, and for a long solenoid phi is equal to, we just derived for a long solenoid phi is equal to mu naught n square pi r square Li. Okay, we just derived this. So if phi is equal to Li and phi is equal to mu naught n square pi r square Li, that means for a long solenoid L is equal to mu naught n square pi r square L. Okay, so in general the flux through these circular loops depends on a geometrical parameter L, which is called the inductance of the solenoid, or inductance. These are called inductor because they have inductance. Why these are called inductor, we will just discuss shortly from now, but it is called an inductance of these inductors. A solenoid is an inductor, a small circular loop is an inductor. So flux through an inductor is given by Li, phi is equal to Li. L is the inductance of the inductor. Okay, now this is a very simple, but very not simple, but this is a, it seems difficult, but actually it is very simple. Excuse me, the concept of self inductance. Now suppose I have a battery and the loop is open now, and at t is equal to 0, okay, at t is equal to 0, I close it. So at t is equal to 0, I was equal to 0, and now the current starts flowing inside this inductor. It cannot instantly become the maximum value I. Suppose it after some time it becomes I is equal to I. So at time t is equal to t, so when I close this, the current is 0 initially, the current starts to increase, the current starts to increase, the current starts to increase, and it becomes I after some time, okay. So notice that I is equal to 0 when initially, and it has increased to some value at time t, okay. So when I pass a current I, okay, then there comes a flux. Initially there is no flux because the switch is open, but when I close this switch, because of the current which is flowing, the current is starting to flow inside this inductor, and because there is a current, there is a flux. Flux will be equal to Li, okay. Now what is happening? As I is increasing, I is so, because of, notice, because of this current there is a flux, okay. There was no flux earlier because there was no current, but because of this current there is a phi. So phi is because of the current which I am putting here, okay. Now current is increasing, okay. Current was I is equal to 0 initially, and it has increased to I is equal to I at time t. Current is increasing, that means flux is also increasing, okay. So now flux also increases. So flux increases means there is a change in flux. So there is a change in flux means there will be an induced EMF from length minus L. So if I just put E is equal to minus d phi by dt. So L will be constant because it just depends on the geometrical parameters. I am not changing geometrical parameters, I am changing just I. I is increasing, only I is changing. So this will be equal to minus L di by dt. So EMF is increased, there is an induced EMF, okay. Flux is changing, okay. Flux is changing. So from Lenz's law, there will be an induced EMF which will oppose this change in flux, okay. From Lenz's law, the flux is changing because current is changing. So from Lenz's law, there will be an induced EMF which will oppose this change in flux, or it will oppose. What is the cause of that flux? The cause of that flux is the current, okay. The current is the cause of that flux. So there will be an induced EMF which will oppose the cause, okay. So there will be an induced EMF which will oppose this current, okay. And what is the cause of this current? This V is the cause of current. So there will be an induced EMF which will oppose this potential V, okay. So notice this, okay. There would have been no induced EMF had there been no flux, and there would have been no flux had there been no current, okay. Because of that current, that flux was produced, okay. Because of that current, that flux was produced, and because of that flux, now that flux itself is opposing this current. The current was the cause of that flux. Now there is an induced EMF which is opposing its only cause, which was the current, okay. That is why it is called self-induction. This current, okay, this loop, the current which was causing this flux, now that it is opposing its cause itself, okay. That is why it is called self-inductance. It is opposing its own cause, okay. So that is the reason why it is called self-inductance. So this L is also called the self-inductance, because of there is an L, whenever I try to pass a current, it will oppose it. Okay, why it will oppose it? Because this current will produce a flux. This changing current will cause a changing flux, and it will oppose the changing flux, so it will oppose the current itself, its only cause. So that is why it is called the self-inductance. So in next videos we will discuss some circuits which have this self-inductor inside those circuits, which are also very similar to the circuits which we studied during our current electricity capacitors. If you had understood those capacitors circuits, they are all same methodology, same steps, and it will be should be straightforward and easy to go through them. So see you in the next video.